35 years with Arslev, which was when I started just a small company, but now is the biggest contractor in Denmark. Then I've been 30 years with standard work, and until this Eurocode, the Eurocode and the national analysis have been part of the work from the Danish standard body. And we had the same problem as everybody else, that the Danish standard body asked people to pay for doing volunteer work. I never paid, but this has changed, not that I'm paying that, but lately for the new Eurocode, it is the Danish Authority of Social Services and Housing which has taken control of the writing of the national analysis. And they have hired people, and they are paying them. Well, today's agenda, there are 4 points. I'll talk about the verification of rotation of sheet piles, and to me, a retaining structure is not finished. The design is not over until you have told the production what profile with what steel posts to use. Similarly, if you do a pile design, you have to tell what is the concrete, what is the reinforcement in this pile, especially when we talk about piles in soft soils where there's an interaction between the soil and the structure, buckling issue. So you have to be involved with the material as well as the chemical matters. I'll speak a little bit about the corrosion issue, and the buckling is just mentioned here that the partly embedded piles, they are covered by Eurocode 3 Part 5. Partly embedded means that it is mainly subjected to bending, whereas the fully embedded piles are mostly subjected to compression. Buckling is not an issue for tension pile, as you probably know. Lately we have these, well, I don't know what the English word we call it in Denmark, Siamese twins. They're born in one piece and they were split into two. The rock bolts and the soil nails are now in 2 separate tractors. And the rock bolts and soil nails are not included in Eurocode 3 Part 5. The steel people didn't want them. They are orphans. They're not a part of a piling or retaining structure. So that was the main reason for the steel people not to involve them. But that doesn't mean that the working groups in Eurocode 7 had to refer to somewhere how to document the steel. So Natalia and the group referred to Eurocode 3 Part 5 regarding the capacity of anchors and tension piles to find the equations and rules how to do that. And I find it will work. Well, back to this verification matter. It's about rotation capacity, and it's the extra rotation beyond the elastic capacity, which is interesting. So it's termed the total rotation minus the elastic rotation. The left-hand side concerns the geotechnical part, and the right-hand side concerns the structural part. But this principle is verification valid is for any kind of retaining wall calculation. Can I point with this? Okay. No, this is not a gamma, it's a Y for yield. It is the elastic rotation, considering the section to be pure elastic up to the semi-plastic limit. It's a trick. It's an approximation, but it makes the calculation easier. And you see, phi CD, that is the plastic capacity of the cross-section. So we have the elastic and the plastic. Reduction factor, rho C, depends on the relative slenderness of the flanges of the sheet pile profile, and it's experimentally determined. You can also use a measure how plastic it could be. We see here cross section class 2 is pure plastic. Cross section 4 or 3 is pure elastic. But cross section 3 is actually everything else between pure plastic and pure elastic. And that's a trick to utilize. It's quite obvious that this profile here has rotated more than this here. That's the idea. Well, I'm talking about the LEM calculations. That's the limit equilibrium method, which anticipates pure active or passive earth pressure distribution. There may be an earth pressure distribution, even if there's no yield hinge. Remember that a yield hinge is a hinge, but with full bending capacity. It's not like a knee where you prop the lid on. It still has capacity. You see in number 3 and 6, there's no yield hinge. The wall is rotating as a stiff rigid body. Could actually be a class 4 section. But still, there might be a pressure jump. In number 1 and 2, it is the anchor, the seal, which yields all the passive pressure in front of the dead man, or the concrete plate, which yields. And by this, allows for active pressure to mobilize and passive. It's only in number 4 and 5 we actually have 1 yield hinge, and here maybe 2. Here it's rotating about the fixed anchor. The necessary rotation depends on the necessary displacement to mobilize plastic earth pressure. The question is how much displacement and rotation is needed. And here we have some guidance from the Eurocode 7 part 3. The ANIC allows for national practice, but typically the mobilization, this rate of movement compared to embedment depth, this be between 0.1 and 0.23% for the active pressure and 1 to 5% for the passive pressure. Typically, you need 10 times as more displacement to mobilize passive pressure than compared to the active pressure. It is quite recognized. Try to show it here. We have different wall heights. Of course, it's the same displacement, but they are giving different rates of displacement compared to the bed wall height. But if we believe that the rate to mobilize the passive pressure is 10 times more than to mobilize the active pressure, well, then this lambda p will be most critical if the embeddment is higher than 10% of the total height, which is very likely. So it's very often it's the passive side which is decisive. You can consider a rotation point on any point. Here it's rotating about the anchor point and also about the embedment point, fixation point. Here the wall is rotating about the point above the soil, and here it's rotating about the fixed angle point. Rotation termed here, it is typically, practically very close to the deformation divided by the height here. And this is what is termed phi WED in Unicode 3.5. I'll show it on the next slide as well. Maybe I should just show the next slide where you can see it, compare it to what is stated in Unicode 3.5. These equations are stated in Unicode 3.5. They are from NHC 4. You see that W1 is actually the displacement where the bending moment is 0. Same as W3, whereas W2 is the maximum displacement. That's very close to, I made different calculations. It seems that if you compare it with if you take the W1 is the deflection of where the anchor point is, then that is 0. That's easier. And then you get a small deviation, but it's very insignificant, the difference to do so. So it's very easy to do so. The formula for the elastic, that is for the elastic rotation, that is the exact solution for a simply supported beam with a uniform load, taken as an approximation for a sheet pile wall. But it's fairly good, even if the load is triangular. It seems to get a very, very good result to use that. Yeah, the term beta here, beta D, it is a reduction factor taking account for the lack of shear force transmission in the interlock and oblique bending in a double U pile. It is 1.0 for set piles, and it's tabled in Unicode 3.5. You can go in there and find it there. I have to go a little back to explain what is this cross-section classes. This is a table from Unicode 3.5, table 7.2. You see they have defined a kind of relative slenderness. It is the width of the flanges divided by the thickness of the flanges, and then weighted by a factor which is taken into consideration the yield stress of the steel compared to the minimum yield stress. So the higher strength of steel, the higher relative slenderness, and the more likelihood of buckling. So when the pile buckles, it is the compression flange that buckles. Therefore, it's quite logical to use the term with beta, the flange width divided by the thickness of the flange as a measure of this. You see, for class 2 sections, they can be utilized 100% plastic resistance. For class 3 sections, they can be used 100% elastic, but anything between 60 and 35 is it's actually also class 3, and there we have the partly use of the plastic resistance. And for U-piles, it's between 49 and 35. Class 3 is not given a value. And the reason is that it's class 3, it's only determined as class 3 when you have documented rotation capacity. And therefore, if you look up in the sheet pile catalogs, you will never see listing of class 1 sections. It's impossible. You have to do this exercise to make it class 1. between these limits of 35 and 60 and 49, the U and Z power bending tests have been determined to reduce, to determine this reduction factor up here. And it is between 1.0 of course and 0.85. And it's, if you take a long row of sheet piles and compare the plastic modulus with the elastic modulus, it's nearly very close to 0.85. So it's not a coincidence that this is the value, minimum value. So if it's 0.85, that is corresponding to a pure plastic cross-section. This is just something from the background developments of Eurocode 3.5 regarding this classification and also determination of the rotation capacity of the piles. It's been carried out for this subcommittee 3 team and a working group A team where I was taking part as a liaison officer. The people involved was Cecil Prim from ArcelorMittal and Dirk-Jan Peters from Royal Haskonik and Colin Jacobs from Anker Schröder in the UK, and also a student, Alexander Enders from Technical University in Stuttgart. And the work of the research group has led to diagrams to determine this rotating capacity from a given slenderness ratio, which I'll show you on the next slide. These diagrams are actually what is written in the current Eurocode 3.5, maybe with slightly changed limits down here, but it's the same structure of the figures. However, this project team 13, they prepared a new format of the figures, but based on exactly the same numbers. And they did it in order to ease of use. Not ease of use to me, because I was getting used to use these curves, but maybe they are right when I show it to you. It's the same. There's one curve for each cross-section. For instance, if we look at the 135, it has a slender ratio of 35. That is purely depending on the cross-section, the geometry of the cross-section and the steel quality, of course. Then for different degrees of utilization of these plastic bending moments, you can go in here at 90% with this, then you get a rotation capacity of between about 0.07 radians. So it's easy to use, and there's one line for every number of slenderness, so you can just round up or round down to determine it. There's also one for Z piles, a little different. You can see, maybe we call it the limit for pure plastic class section class 2 is 35. So everything below 35, 25, we have a possible utilization of 100% of the plastic resistance. But when we go above 35 slenderness, it decreases. Let's take a simple calculation example. It's a wall with one yield hinge. I just have to go to my notes. I used the Brink-Hansen theory, but it's actually not important which guru you use. The most important that it is a limited equilibrium method to use the plastic calculation. There's a pressure jump just below, just above the anchor. You can see it up here. It's a pressure jump. And there's a 5 meter differential water pressure. There's a sand above the clay. There's a hydrostatic pressure, but we have disregarded the seepage around here, so it's hydrostatic all the way. And this has been done before we knew about the profile. But in order to check the rotation capacity, we have to investigate the profile. And I chose a AZ 18700, high steel quality. This gives a slenderness ratio of, say, 45. They will remember 35 was class 2, but anything higher than 35 is class 3. So this is a class 3 cross section. And if it's a set profile, then this beta values are 1. And I've calculated the plastic and elastic bending resistance. I've used the Danish part coefficient of 1.1, but that's not important. The important is that you can see that the actually the design bending moment is bigger than the elastic. So we have to utilize some part of the plastic bending moments. That's necessary in order to use this profile. By the way, I just took the rate between these two, and it is, as stated before, 85%. Now the question is it possible to utilize it 88%, which is needed here, the plastic? And I want to use the plastic bending capacity 88%. Well, if we go into this, it was a lambda value of the slenderness ratio of 45. We go in with 88%. Yeah, it's possible, we can see, and we have a rotation capacity of say 0.045 meters. That's it. Piece of cake. You could also use the old format, the table. Then you interpolate. We have 85 and 90 and 88% here. You go in with a lambda value of 45 and go out, and you find exactly the same. So actually the former graphic determination is okay compared to this one. Now what happens if you choose a cross-section which has an even lower value than 85% of utilization of the plastic moment? Well, in that case you could choose the 85% curve. That's on the safe side. However, if the profile is much stronger than you need, then you will face that it is not the seat part which is yielding, but it's so strong so it pulls the anchor out. And if the anchor is a grouted anchor, it may fail because it's not as ductile as an anchor for detonating. So take care not to choose too strong profiles. You have to be loyal to the model that you're working with.
Ole, are you still in time? Because
yeah, well, I have
got 3 other subjects.
Yeah. Okay, I have 6. No, I have. There's 22. This is number 22. I have 26.
Okay.
Fine. Yeah. Well, this is just to show the example. I guess this will be published afterwards. I assume this 5% deformation is 200 millimeters, but still this 200 millimeters gives you a necessary rotation of 22 degrees. And if you subtract the elastic one, you get 0.42 degrees, which is much less than the capacity. So this is the exercise to prove that you have enough rotation capacity. But it's important to choose this value, because if it was a little less, then this value may not even have been above 0, which would have meant that even the elastic rotation would have been enough to do to give the enough lubrication capacity. Okay, then I'll go to this about the durability of the. This is for which is written in EUCO 3.5 anchors. There's a little bit different here. We say, I think Natalia was also touching this in her presentation. The steel code says that we have to be below 500 megapascals in order to use sacrificial thickness for corrosion protection. And this has been changed in EUCO 7 Part 3 to 600 megapascals. But I guess that's the free choice of the working groups in EUCO 7. They can change it. I just make attention to there's a mismatch here, and it's the same for the rock bolts and the rock surface. Yeah, that's it.